Welcome to Lecture 14 of Microeconomic Analysis 1 with me, Dr. Craig Webb. In today's lecture, which is the final lecture of this semester, we will be looking at the firm's costs in the long run. To do this, we'll be using the tools we've developed in long-run production, so ISO quants, marginal rate of technical substitution, and introducing new tools such as ISO costs and expansion paths as we discuss the cost minimization problem with a view to constructing the firm's long-run total cost function. So lots to do today, so let's get started. Let's begin with a quick recap of some of the material on long-run production that we introduced in Lecture 12. Remember, the definition of the long run is that the firm is able to vary all inputs, so both labour and capital are variables. We're not assuming that these are fixed. The firm can choose any quantity of these variables. The connection between choosing these inputs and how much output the firm is producing is described by the long-run production function. So we write output Q is equal to some function f, which is the long-run production function, which takes inputs labour, capital L, and capital K. Of course, if we use different combinations of L and K, it may be the case that the same amount of output is produced. So we could lower the level of labour and increase the level of capital in our factor combination and still produce the same amount. To represent this diagrammatically, we use the notion of an isoquant. So an isoquant is a curve connecting all of these different combinations of labour and capital that yield the same level of output. Mathematically, I could write this as a set. So it is a set, I use curly braces, of all of the different combinations L and K, these pairs, factor combination pairs, that satisfy the rule. When I plug them into the long-run production function, out pops the same level of output. The slope of an isoquant in factor space is telling us the rate at which we can exchange one factor for another, so exchange capital for labour, whilst maintaining the same level of output. And we gave this a name, the marginal rate of technical substitution. We showed in Lecture 12 that this was equal to the negative of the ratio of marginal product of labour over marginal product of capital, where the marginal product of labour is the partial derivative of the long-run production function with respect to labour, and the marginal product of capital is the partial derivative of the long-run production function with respect to capital. Here in this diagram, I've drawn some typical isoquants. So we have three isoquants. The lowest of these, or the isoquant closest to the origin, is all of the different combinations of labour and capital that produce output Q bar 1. And then above this we have an isoquant labelled Q bar 2. And above this we have an isoquant associated with output level Q bar 3. We make several assumptions about isoquants, so we will assume frequently that they are downward sloping, they're perfectly thin, that they don't intersect, and most commonly we will assume that they are convex. That is, they start off very steep and get flatter as we increase the amount of labour. Or another way of saying this is that the marginal rate of technical substitution is diminishing. Here I've identified the marginal rate of technical substitution at a particular point, this yellow point, which would be the slope of a line tangent to the isoquant. So this green line, which is tangent to the Q bar 3 isoquant at that point, the slope of that green line would be the marginal rate of technical substitution at that point, meaning the rate at which I can exchange capital for labour whilst maintaining the same level of output. Now let's begin our discussion of costs in the long run. So we're going to assume that the firm is using two inputs, labour and capital, and that the prices for these factors of production are given to us. So they are fixed numbers, which we will call for labour the wage rate W. So each unit of labour L is costing the firm W. And for capital, we'll refer to a rental rate. We'll denote lowercase r. So for each unit of capital, it's costing the firm lowercase r to rent that capital. Now, if a firm employs L units of labour, which could be measured in hours, for example, then I multiply the number of units that are being used by the wage rate W, and the cost of labour is then W times L, or just WL. If a firm employs K units of capital at a rental rate R per unit, then the cost of capital is R times K. So, based on this, we can calculate the total cost of any input combination, so a pair which has some L in it and some K in it. If we look at this input combination, we can calculate its total cost quite simply as some number C, the cost of this input combination, is equal to W times L, the total cost of labour, plus R times K, the total cost of capital. Now notice that this is simply the cost of the input combination. When we talk about cost functions, as we've done in the previous lecture, and as we will work towards in this lecture, cost functions are functions of output. So when we talk about the total cost function, it will be telling us something about the cost of output. Okay, so this C here, the cost of an input combination, is not the total cost function. It's simply an amount of money that refers to the total cost of a particular input combination. Now, when we construct the total cost function, we're going to have to optimize our choice of this input combination. Okay, so that's what we will work towards today. A tool that we will make extensive use of as we work towards solving this cost minimization problem we'll discuss next, and the construction of the total cost function, a function of output. A tool that we will use a lot is called an ISO cost. So as with ISO quant, ISO means single. So ISO cost is a line which is going to connect all different combinations of labour and capital that yield the same total cost. Notice I say it's a line rather than a curve because we have a very simple linear equation to describe an ISO cost. So I could label one particular ISO cost as a set of all the different combinations of L and K with the property that their cost, WL plus RK, is equal to some constant. So here I've put C bar overlined C. Consider this diagram now. This shows three ISO costs. I've labeled the ISO cost lowest or closest to the origin is the ISO cost of all of the different combinations of L and K that yield cost C1. The next ISO cost is all the combinations that incur cost C2. And the ISO cost I've drawn furthest from the origin is all of the different combinations of L and K that incur a total cost of C3. Okay, so these are downward sloping, perfectly thin, straight lines, very similar to budget lines. And indeed, the slope of these lines, so the derivative of capital with respect to labour, restricting attention to an isoquant, is simply the negative of the ratio of prices. So we've seen this before. You could prove this yourself. The slope is minus the price of labour over the price of capital. So minus W over R. Now let's discuss the firm's cost minimization problem. So remember that in general, when we look at an isoquant, there are many different combinations of labor and capital that all produce the same amount. Also, each of these combinations may well have a different cost. So, when trying to produce a certain amount of output, the firm wants to do this as cheaply as possible. In fact, it's a necessary condition for profit maximization that the firm minimizes the cost of its production. Okay? Now, when we say minimizing the cost of production, this has a specific meaning. Clearly, just employing 0 units of labor and 0 units of capital incurs the minimum cost. That would just cost 0. However, that's not what we mean by the cost minimization problem. The cost minimization problem is this: fix a target level of output. Here I've denoted it Q bar. This is our target level of output. And then the cost minimization problem is to minimize the cost of the factor combination that's being employed, subject to the condition this combination of input factors does indeed produce the target level of output. Okay, so I take a target level of output Q bar and then find the cheapest way of producing that target level of output. Mathematically, we can write the problem minimize by choosing L and K, the cost W times L plus R times K, subject to the constraint F of L K. So if I plug these values into the long run production function, out pops the target level of output. Okay, so that's a mathematical way of describing the cost minimization problem. Another way of describing it graphically could be the following: the target level of output is associated with a particular isoquant. So I could phrase the cost minimization problem as subject to achieving or subject to being on that particular isoquant, I want to choose the factor combination on the lowest iso cost possible. Okay, get onto a particular isoquant whilst minimizing or being on the lowest iso cost, the iso cost closest to the origin. Okay, so this is a familiar constrained optimization problem. So let's move on to paper now, and we will formulate the problem, examine the Lagrangian for this problem, and derive the first order conditions for solving this problem. Okay, so let's have a look at the firm's cost minimization problem, and we'll approach this using calculus. So remember, the problem is to minimize by choosing an amount of L and an amount of K, the cost W times L plus R times K. So get onto the lowest iso cost possible, subject to the condition and we have a target level of output. So when we plug these values of L and K into the long run production function, we should get our target level of output, which we denoted Q bar, just to denote it as a fixed amount. Okay, so this is the constrained optimization problem. Minimize this function subject to this constraint. And we've seen constrained optimization problems before. The way we tackle this is to form a Lagrangian as follows. So the Lagrangian, we do this fancy L, is a function of L and a function of K. And it's also, we introduce this additional variable, the Lagrange multiplier lambda. So this would be equal to the thing we're trying to minimize, WL plus RK, and then we add lambda, and here we do the difference between Q bar and how much is actually being produced. So this is the thing that we want to be 0. So Q bar minus F of L K. Okay, so that's the Lagrangian for this problem. It would be the same for a maximization problem as well. So you use the same techniques. It's the second order conditions that change for for optimization problems. It's not the first order conditions that change. So what do? Well, we partially differentiate the Lagrangian with respect to L, okay, and we partially differentiate the Lagrangian with respect to K, and we partially differentiate the Lagrangian with respect to lambda. Okay, so we get each of these partial derivatives, and then we want to find the particular L star, K star, and lambda star that make all of these equal to 0 simultaneously. Okay, so that would be the first order conditions. So let's actually take these partial derivatives. The partial derivative of the Lagrangian with respect to labor would be W multiplied by what we called, so just W, and then a minus lambda. And here we'd have the partial derivative of this long-run production function with respect to labor. We gave that the name, the marginal product of labor. Okay? And we want this to equal 0. It doesn't always equal 0, but when we've solved our problem, we've chosen the particular L star, K star, and lambda star, then this will equal 0. So 0 at the solution. The next condition would be if I differentiate the Lagrangian with respect to capital, I would get R minus lambda, the marginal product of capital, and at the solution, this would equal 0. Okay? So if I take these two equations together, what do I get? Lambda appears in both of them. So I could write this as, I could write this first one here. Let's get lambda by itself. So W over MPL equals lambda. Okay? I guess lambda star would be the appropriate, because we're talking about the optimal solution here. And in this equation here, I would get R over MPK is equal to lambda star, okay? Which means these two things are equal to each other. So taking these together, taking this and this, with some slight rearranging, I could get minus MPL over MPK, which is equal to the marginal rate of technical substitution, would have to equal minus W over R, okay? So what's this saying? The marginal rate of technical substitution, the rate at which I can exchange one input for another whilst maintaining the same level of output, has to equal minus W over R. And this is the rate at which I can exchange one input for another whilst maintaining the same cost level. I'm not sure it has a specific name, but it's graphically, we're saying the slope of the isoquant is equal to the slope of an isocost. So this is a tangency condition, okay? I'll produce a diagram after this. So there's our first equation. We've got two unknowns, L and K. So there's our first equation. And then our second equation, if I partially differentiate the Lagrangian with respect to the Lagrange multiplier, and set that equal to 0, I'm simply saying that this is the same as saying that Q bar is equal to F of L star and K star. Okay, I'm using the stars because I'm saying this derivative is not always 0, but at the optimal solution, it is 0. So I get two equations. The slope of an isoquant is equal to the slope of an isocost. And secondly, our constraint has been met. These particular L star and K star happen to produce the right amount of output, Q bar. So that's the characterization of the solution to this problem. Here is a graphical representation of the cost minimization problem. Remember, mathematically, the problem is to minimize the cost of an input factor combination, a pair with some amount of L and some amount K in it, and the cost is WL plus RK. We want to minimize that cost subject to the constraint that F of LK, so when I plug this input factor into the long run production function, out pops the target level of output, Q bar in this case. Okay, so that's the mathematical problem. Graphically, the problem is find a pair LK which is on this particular isoquant, which here is a pink curve labeled f of LK equals Q bar. So I want to find the particular LK combination somewhere along that isoquant that is on the iso cost as close to the origin as possible. So I've drawn several iso costs and a downward sloping arrow to indicate the idea that we are trying to get on the lowest possible of these iso costs. As we've shown in our analysis, the solution to this problem is characterized by two equations. Okay, so remember we're looking for a pair L star K star that solve this problem that has two dimensions, an L star and a K star. So if I'm going to characterize the solution, I need two equations. The first of these is very simple. It's simply the requirement that f of L star K star, so when I plug these into the long run production function, they do indeed produce the required amount of output Q bar. So that's our first equation. And our second equation we derived in our analysis previously is that the minimum cost occurs where the slope of an iso cost is equal to the slope of an isoquant. So the iso cost is tangent to the isoquant marginal rate of technical substitution, the slope of an isoquant, which is also equal to a negative ratio of marginal products, must equal minus W over R, so the negative of the ratio of factor prices in this case. As a step towards deriving the long-run total cost function, we're going to analyze something called the expansion path. This is constructed as follows. For a fixed wage rate W and rental rate R, so we're going to take prices for the input factors as given and fixed, we know that a necessary condition for cost minimization is that the following equation holds. Marginal rate of technical substitution, or minus MPL over MPK, is equal to minus W over R, the negative of the ratio of factor input prices. Now this equation is actually satisfied, or may be satisfied, by many different input combinations. Okay, so it was only one of our equations. The first equation in the previous slide that we listed was that the particular combination produces the correct level of output. Okay, but for this equation, marginal rate of technical substitution equals the negative of the ratio of input prices. This may be satisfied by many different input factor combinations. Now, the expansion path is a curve which is going to connect all of these input combinations. So we could say that any point along the expansion path is a solution to a cost minimization problem for some level of output. Okay, so each different point along this expansion path, because it satisfies the equation above, will be a solution, but because they will produce different levels of output, they are solutions to different problems. In general, we'll think of this as increasing, but it can be any shape. So let's have a look at this idea graphically to show what it means. Here, I've just produced a diagram of a cost minimization problem and said that L1, K1 solves the problem, minimize the cost of production subject to the condition that output is equal to Q bar 1. Okay, so this occurs at this tangency point here, marginal rate of technical substitution equals minus W over R. Now suppose I choose a different level, a different target output level. So I want to now produce Q2, Q bar 2, instead of Q bar 1. The solution to the cost minimization problem changes. Okay, so I now need to choose a different input factor combination that is on a higher isoquant. But this particular solution to this second problem will still satisfy the equation marginal rate of technical substitution equals minus W over R, because it's a solution to the cost minimization problem, and W and R have remained fixed. Again, I've drawn another cost minimization problem, and you can see here that L3, K3, this input combination, will solve the cost minimization problem given W and R if the target output level was Q bar 3. If I draw a curve through each of these points, you could see that every point along this curve is going through a point where the equation marginal rate of technical substitution equals minus W over R. And we call this curve the expansion path. So given W and R, the expansion path connects all of the different LK combinations that solve a cost minimization problem, but of course they're solving cost minimization problems that have different target output levels. Okay, so once I know this expansion path, you could imagine this is an incredibly useful thing to know, because what it's telling me is it's all of the LK combinations that are in some sense the best ones to use. Once I've decided my output level, so if I want to produce Q2, I just look at where the isoquant associated with output Q bar 2 intersects the expansion path, and by choosing that particular input combination, I would be minimizing cost. If I wanted to produce a different amount of output, then I would just look at where the isoquant for that level of output intersects the expansion path and read off the optimal amounts of labor and capital. So this is an incredibly useful thing to know. Let's do a parametric example now on paper and derive the expansion path for the Cobb-Douglas long-run production function. Okay, so let's let's calculate an expression for the expansion path for the Cobb-Douglas long-run production function. So we know this by now, that the long-run production function, the Cobb-Douglas case, is Q is equal to some constant capital A multiplied by labor L to the power alpha multiplied by K to the power beta, where A, alpha, and beta are greater than 0. Okay? We know that the sum of these is interesting, so if alpha plus beta is equal to 1, that's the constant returns to scale case, etc. So we know quite a lot about this long-run production function by now. Okay, so let's calculate the expansion path. Now remember, the expansion path is characterized by the condition that every point on the expansion path gives a pair L and K that satisfy the equation the marginal rate of technical substitution at that point is equal to the ratio of the negative of the ratio of input prices. So we need to know the marginal rate of technical substitution. So let's just quickly recall that. I think we've done it before. So marginal rate of technical substitution is minus MPL over MPK. Okay. So what are these expressions? Well, MPL, the marginal product of labor, which is simply the partial derivative of the long-run production function with respect to labor. In this case would be, so assume K is constant and take the derivative with respect to L. We get alpha A times L to the power alpha minus 1, K to the power beta. Okay. And the marginal product of capital would be a similar expression, but using partially differentiating with respect to capital. So I would get beta times A, L to the power alpha, K to the power beta minus 1. So the marginal rate of technical substitution would be the negative of this expression divided by this expression. Now a lot of things will cancel out. This A will cancel out with this A. Here I've got alpha minus 1 being divided by alpha minus 1 and then another So I'll have L on the bottom. So we'll have alpha over beta. I've got more K's on top and more L's on the bottom. So K over L. So this is the marginal rate of technical substitution for the long run production function of the Cobb-Douglas form. Okay. Now the cost minimization problem gave us the condition that MRTS equals minus W over R. Okay. So in this case, we get minus alpha over beta, K over L is equal to minus W over R, right? So that's this equation will hold whenever we're cost minimizing for all different target levels of output. As long as we have an interior solution, this is one of the equations that will hold when we're cost minimizing. So this is this is what we need for our expansion path. Now, when we draw a diagram of the expansion path, we're drawing it with labor on the horizontal axis and capital on the vertical axis. So to get the equation for the expansion path, I simply need to get K by itself in terms of L. Okay, so the equation for the expansion path in this case is going to look like this. K equals something. I just rearrange this. I would get beta over alpha W over R multiplied by L. Okay. Now, don't be fooled by the fact that there's lots of terms here. All of this here, these are just constants. So this is a constant divided by a constant, multiplied by a constant, divided by a constant. This is just some number. K is equal to some number times L. So the expansion path here is linear. Okay, it's just a straight line. So I've produced the diagram here. If we have a look at it, the two purple curves are two different isoquants, which are tangent at these yellow points to isocosts. So the lowest of these yellow points solves the cost minimization problem when the target output level is Q bar 1. The second yellow point solves the cost minimization problem when the target level of output is Q bar 2. And I know, because the expansion path has the equation K equals beta over alpha W over R times L, that these lie on a straight line. So I've drawn this green straight line as the expansion path for this Cobb-Douglas function. This is another reason why the Cobb-Douglas function is so widely used. We get this derived concept. We're talking about a function generated as expressing a relationship between variables as they solve a constrained optimization problem. How wonderful that they all happen to lie on a straight line. Okay, so this does not always happen, but for the Cobb-Douglas case, we get a linear expansion path. So now that we understand the cost minimization problem, we know how to solve or to characterize the solutions to this cost minimization problem, and we know the expansion path, which connects all the different possible solutions for different cost minimization problems, taking the prices of inputs as fixed in each of these problems, just varying the target level of output. So now we know enough to construct the long-run total cost function. So this is how it's constructed. The long-run total cost function, C of Q, it's a function of output. So I'm plugging in a level of output, and out pops the cost associated with that output. But most importantly, it's the minimum cost. So the long-run total cost function evaluated for output level Q, C of Q, tells us the minimum cost associated with producing that level of output Q. Okay, now we could write this C of Q is equal to W times L star as a function of Q, so the optimal amount of labor associated with that target level of output, plus R times K star as a function of Q, so the optimal amount of capital associated with that target level of output. How do we do this? Well, if we look only at the expansion path, then we know that each input combination on the expansion path is the cost minimizing input combination for a certain level of output. Okay, so if we are interested in output level Q, then we find the point on the expansion path where the input combination at that point produces output Q, and then we'll write this point as L star as a function of Q and K star as a function of Q. Then we simply calculate the cost of this input combination, so multiplying L star by W and multiplying K star of Q by R and summing up these costs. If we continue in this way for all different output levels, we can construct the entire long-run total cost function. So let's just describe this graphically. If I'm given W and R, so I'm given the input prices, the prices of these factors of production, and these prices are fixed. So W and R are fixed. If I'm interested in a particular level of output Q, so I've got this pink isoquant, and I know that every combination along that isoquant produces output Q, then I look at where this isoquant intersects the expansion path, which is at the point labeled L star of Q and K star of Q at this yellow point. And at that point, I know I'm cost minimizing. I'm producing that output in the optimal way, in a way that minimizes the total cost of producing that output. I'm on the lowest possible ISO cost subject to actually producing output Q. Then, to get the value for the long-run total cost function, I simply take the cost of that particular input combination. So C of Q is equal to W times L star of Q plus R times K star of Q. Okay? Again, if I wanted to choose a different output level, I could follow the same algorithm, and doing this, I could construct the long-run total cost function for all conceivable levels of output. Once I know the long-run total cost function, I can then derive many of the related cost functions, the marginal cost, average cost, and so on, all of which are so vital for the firm's decision-making in the long run. So there we have it. That's the derivation of the firm's long-run total cost function. This is crucial for the firm to know, as in any market that it operates, the firm always wants to maximize profits. It does so by using the marginal cost function as part of its decision-making, and it needs to make sure that it's making non-negative profit by using the average cost function or the average variable cost function in the short run. So this will all become clear as you study semester 2 of microeconomic analysis. As you study different market structures, the way that the price is determined in a market, which you could think of as the inverse demand function, that's going to be different in every market. What will remain the same are the firm's costs and, of course, the objective of the firm. Wherever it finds itself, whether it's in a competitive market, a monopolistic market, a duopoly, oligopoly, and so on, in each of these cases, it's always trying to maximize profit. This is the only objective of a firm in microeconomics, and it does so by comparing revenue and costs. So now we know a lot about costs. In your next semester, you can look at the different inverse demand functions for all sorts of different markets. So I wish you all the best. In the meantime, take care.